Good morning. My name is Mackenzie Woodman. I'm the Remote Sensing Application Specialist here at Spectral Evolution, and today I'm going to be discussing remote sensing methods for water quality. Spectral Evolution is the leading manufacturer of high-quality UV-Vis NIR spectrometers and spectroradiometers for environmental remote sensing, mining, and laboratory applications. They've been around since 2004 and are located in Haverhill, Massachusetts, so the Boston area. The primary applications for our spectroradiometers are in hyperspectral applications, remote sensing and vegetation, mining and geology, as well as photonics and calibration transfer. Now to discuss water quality and remote sensing and why it has become such a critical tool in research. Water quality affects the surrounding communities both economically and in public health. It is linked to fishing industries, tourism, and even drinking water, and it can be used in water scarcity research, environmental impact, and climate change studies as well. Oftentimes, water bodies are large systems and require continuous monitoring, which makes remote sensing such an effective tool because you can incorporate satellite data as well as field data in order to sample a large dynamic system. So what is water quality remote sensing, and what are the parameters that most scientists are looking for? The most common studies are in algae bloom detection, acid mine drainage, turbidity, organic matter, tracking pollution, chlorophyll content, and water management applications. All of these can be studied on the small scale with water samples and a field spectrometer, but many are studied using remote sensing satellites or drones along with a field spectrometer or spectroradiometer. It is critical to quickly identify what is in the water and how it is changing on a large scale. Sending scientists into the field to collect water samples on a boat is both time-consuming and expensive, and often leads to small sample sizes comparatively to the large systems that are being studied. As stated before, there's many constraints on water quality sampling, and these are primarily derived from the satellites and the actual water body physics for remote sensing of water bodies. So water is a really good absorber of light, and so you'll be operating with very low light conditions or low signal conditions, which brings the field spectrometers and especially the satellite spectrometers or spectroradiometers to the brink of their capabilities. So there's many different methods to deal with things like sun glint that I'll be going over today. Here on the right we have a remote sensing image of a water quality study done through the NASA's Delta X program. They used a 1100F to do their ground validation, which brings me to the point of all of these water quality remote sensing techniques using satellites. They'll typically have a coarser spectral and spatial resolution, and so especially when it comes to water quality, they necessitate some amount of ground validation or ground truthing in order to really understand your data and the maps that you're creating or generating through these remote sensing techniques. So the instrument that I primarily recommend for ground validation and ground truthing is our PSR 1100F. This will allow you to do most of your studies on algae and biomass in the water system. When you're doing studies that relate to what kind of turbidity, what kind of mineralogy are you looking at in the water, some of the acid mine drainage applications, then you're going to want to have the full spectrum, so that would be a NatraSpec. But the PSR 1100F performs great for algae quantity applications, chlorophyll content, and that kind of thing. And this is an example of taking field measurements off of the side of a dock. Now here you can see 4 different examples of the PSR 1100F out in the field. As you can see, it can be used off of the side of a boat, as well as in estuary systems, marsh systems, and it can quickly adapt to be used for leaf analysis or with a leaf clip. All of our accessories are compatible with the 1100F, and its spectral range is 320 nanometers to 1100 nanometers. When collecting reflectance data off of a water surface, a lot of the signal that you're collecting will be the sky's reflectance, or the sky's reflection. So in order to compensate for that, you have to use what's called a remote sensing reflectance, or calculate what's called a remote sensing reflectance. And this will use an irradiance calibration, so typically this is done with a spectroradiometer. So your signal is S, W plus S. That is the measured signal from the water and includes both the water leaving radiance and the reflected skylight. The sky is the measured signal from the sky, and SP is the average measured signal from the white plate. So that would come with your spectrometer. And then REFL is going to be how much of your reflectance is, so the spectralon's reflectivity, so that'll be 99%, and then pi here. And then the measured sky radiance is then multiplied by a proportionality factor that relates to radiance measured when the detector views the sky to the reflected sky radiance measured when the detector views the sea surface. This can be found in a table in Mobley et al. 2015. This is widely cited as a way to calculate remote sensing reflectance. And here on your right, you can see the actual equation for remote sensing reflectance. So you're not just taking a ratio or collecting just a straight reflectance measurement. You're going to want to take measurements approximately 90 degrees at azimuth angle to the sun and at a 40-degree angle relative to vertical to minimize reflected sunlight. So you're going to actually angle yourself to minimize the amount of sunlight that's contributing to your scan. So an example procedure for this kind of measurement is to first determine the solar plane and zenith and orient the boat so that you can take the measurement at a 40-degree angle from the solar plane. So here you can see the figure on the right. And then using your radiometric calibration, and typically with a lens, because a smaller field of view will help mitigate some of that solar reflection, you can take a scan at a 40-degree angle with a white plate and then rotate it 180 degrees and take a scan towards the sky at a 40-degree angle. And then these measurements are taken at 90 degrees and to 135 degrees azimuth angles. Now, those of you that have conducted water quality testing have often or are likely to have seen a Secchi disk. So Secchi depth is something that's used as a proxy for turbidity and water clarity. You essentially lower the disk or bring it back up until you can see the checkered pattern on it. And this depth will tell you how far light is penetrating typically. So the average percentage transmission of surface light at a Secchi depth, which is one depth to where you can see the Secchi disk, is 14.7% of the light. So when you're doing or conducting remote sensing applications, you can assume that what you're seeing in your scans is less than a Secchi depth, or the majority of it that's contributing to your spectra is less than a Secchi depth. And you'll see 14.7% of that signal will be at a Secchi depth, and will go a little lower than that. But as a quick rule of thumb, Secchi depth is often used as a proxy for what you're actually scanning when taking water reflectance. So here's a quick example of some spectra that we collected out on Conway Lake. And so this is what a typical water quality scan will look like. And as you can see, the reflectance percent is at a very low number. And that's because we're operating with very low signal coming off of water surfaces. We also incorporate spectral indices into our software. So many times in water quality applications, different indices will be used. This could be surface algae bloom index, or NDVI is often used for surface biomatter. These are all things that are incorporated into our software, so you can quickly get an answer for what those indices might quantify, and get an answer while you're in the field taking in situ measurements. So, as I was saying earlier, we did take spectra of the Conway Lake, and so we went out in the field with some researchers out of UNH. They collected chlorophyll samples, and we collected surface reflectance. We then calculated some different metrics using a Landsat 8 flyover that happened at the same time, and we compared what were we seeing in situ versus what were we seeing from the satellite data. And so as you can see, our correlations were higher in the in situ data compared to the satellite data, and that likely has to do with the coarser spectral and spatial resolutions. That being said, this was a small sample size, so we would likely see these correlations increase with more samples and higher sampling in this area. So that brings me to my point of why ground validation is so important. And so these satellites typically have much higher spatial and spectral resolution. They also have lower temporal resolution as well, so the flyovers may not be when you need them, and if there's a bad day, maybe it comes over once a week. If there's a bad day or a cloudy day that day, you may not see sampling for weeks at a time. So by using field spectrometer and field spectroradiometer, it allows for better temporal frequency as well as higher spectral resolution and spatial resolution. So although it's still limited by the weather patterns, there is the ability to schedule around it and go out in the field and collect more data. So when trying to calculate the quantity of many of those water quality metrics, so how much biomass is there, how much chlorophyll, how much turbidity, what is the total suspended solids, oftentimes researchers use what's called a partial least square regression. So what this does is it essentially compares a known set of data, so a calibration set, so it'll have spectra for a known quantity of total suspended solids, in water, and it will match up the spectra for each of those calibration sets. And then when you take scans, it will use that model to predict how much of the total suspended solids is there. So it's a statistical technique that allows you to compare known quantities to spectra, build a model, and then use that model for field samples. And these models are typically limited to the actual quantity of that calibration set. So how much sampling did you do to create a robust calibration set? And it's also limited to how much of your absorption features are in that 350 to 2500 nanometer spectral range for the full range spectrometer or field spectrometer. So that's why these PLSR partial least square regression models are so important to a lot of these different studies, and they're also integrated into our software, so you can port in that model, so when you take a scan it will match it to that model and give you a prediction for different water quality parameters or soil parameters for that matter, or any other research that you may be doing. So this is how our software integrates the model into your sampling protocol. So you can actually take the live scans and it will read out a prediction based on your model that you gave the software. So this still takes a lot of legwork to have the samples collected, but it still has the ability to speed up future sampling efforts. So these models are not limited to just water quality. They can also be used in mining applications or geological applications. So here you can see the XRD prediction is 81.7%, and then the model that was used for these samples predicted 86.6%. So that bit of error there is due to the model either needing more quantity in it or more calibration samples. But it acts as a great proxy for quick sampling without needing to process your samples whatsoever and getting a good prediction on these different metrics. And then here you can see from that same Delta X program campaign, they use a partial least square regression in order to predict total suspended solids. And so as you can see, the higher remote sensing reflectance typically correlates with higher amounts of total suspended solids. So I would expect that that's because the actual light is penetrating less and bouncing off of that turbid water, and you're getting higher reflectance for higher total suspended solids. But they did the same thing here, where they collected field samples of total suspended solids or total suspended sediment, and then they created a model that they could use to match to their reflectance. And these same models can be used to quantify chlorophyll, A, CDOM, and other turbidity metrics as well. So without the use of statistical models, you can conduct algae speciation studies. So these are commonly using the reflectance spectra of the algae in the water and identifying what species of algae that's likely to be. Each algae has a unique kind of chlorophyll as well as pigment products within them that can be used to identify algae species. Typically, these algae species can be determined within the 320 nanometer to 1100 nanometer range and have unique features there that can differentiate each other. There are some algae and suspended sediments that can't be differentiated in this range because they have more unique features past that into the full range spectrometers. So from 350 to 2500, you should be able to identify any kind of, or most kinds of species, but for the most part, for biomass and algae, you can determine what species they are based on remote sensing reflectance. Now, this would be done by running regressions against spectral libraries of known algae reflectance and matching that to what you're seeing in a reflectance measurement. So oftentimes, water quality reflectance will require some amount of decomposing of the signal. So sometimes this is done with a principal component analysis, or other techniques, statistical techniques, that allow you to decompose the spectral signal and then use that to identify what algae may be present if there's more than one, as well as suspended sediment in your spectra. So, to conclude, remote sensing of water quality is a diverse and challenging field and research area. It requires the most sensitive instruments because we're operating at very low signal conditions. So it is incredibly important to have the correct procedures and use the correct spectrometer and accessories for the job. And so consider Spectral Evolution for all of your water quality remote sensing needs. And with that, I'd like to say thank you, and I'd like to open it up to any questions that you may have. And feel free to reach out at my email. I'd be happy to answer any questions there as well. Thank you.